Hey guys, today we're going to learn about the relationship between a function, its first derivative, and now we're going to introduce the second derivative. First, let's review some of these relationships between the first derivative and its function. So, if f prime of x is greater than 0, then what that means is that f of x would be increasing. If f prime of x is less than 0, then f of x is decreasing. And this should all be reviewed from stuff that we did way back when. If f prime of x is equal to 0 or is undefined at x is equal to some number, then what that means is that you have either a horizontal tangent, that's when f prime of x is equal to 0, or if it's undefined, that's when you have the vertical tangent. This also means that you can have extrema. If f prime of x changes from positive to negative, that indicates that we have a maximum. And finally, if f prime of x changes from negative to positive, that indicates that we have a minimum. So let's review this process before we start introducing the second derivative. Here we have this polynomial. F of x is equal to x to the fourth minus 4x to the third. In order to determine whether it's increasing, decreasing, or has any relative extrema, we're going to take the derivative, which is going to equal to 4x to the third minus 12x squared. Then we make it equal to 0, and we find our critical numbers. So in order to find critical numbers here, we're going to have to factor. 4x to the third minus 12x squared has a 4x squared in common, which would leave me with x minus 3. If we set each of these factors equal to 0, we would get our critical numbers. For this one here, we would divide by 4, 0 divided by anything is 0, and then square root, which would still be 0. And here we would add 3 to the other side, so x is equal to 3. These are my critical numbers, and now I'm going to create my number line to figure out when the derivative is positive or negative. Always making sure that your number line has your numbers there in order. I'm going to use my factored version here to make determining the sign easier. If I plug in -1, remember you're picking values in between these numbers to figure out the signs. So to the left of 0, I'm using -1. -1 squared would be positive, and then -1 minus 3 would be negative. So positive times a negative would make this negative. If I plug in a number between 0 and 3, such as 1, this would still be positive, and this would still be negative, so this would be negative. And if I plug in 4, a number greater than 3, this would be positive, and 4 minus 3 is also positive, and a positive times a positive is positive. So now let's answer, or rather let's fill in these sentence frames. F of x is increasing on the interval 3 to infinity because this is when f prime of x is greater than 0. F of x is decreasing when the derivative is negative. There are two negative intervals here, but you always have to stop at the critical numbers because when x is equal to 0, that means that the derivative is 0, which is not negative. So we're going to write our interval as negative infinity to 0, and then from 0 to 3, because f prime of x is less than 0. Now let's look at whether we have any maximums. A maximum occurs when you have when your derivative changes from positive to negative, which you can see here it goes from negative to negative and then negative to positive. So we would say here that f of x does not have a relative minimum because f prime of x does not change from positive to negative. Sorry if you can't really see that very well, but it says from positive to negative. Last one here, it says f of x has or does not have a relative minimum. A minimum occurs when it goes from negative to positive, which we do have, so has a relative minimum at x is equal to 3. And we would say here because f prime of x changes from negative to positive. Now let's discuss our critical numbers a little further. What we have talked about, or what we just looked at, was a polynomial function. And in order to find those critical numbers, we set that first derivative equal to 0. What we've looked at in the past is that a function is not differentiable when there's a cusp. But that does not necessarily mean that there isn't a relative maximum or minimum. Critical numbers of a function do not only occur when the derivative is equal to 0, but also when the derivative is undefined. Which is like, if you look at this function here, we have f of x is equal to x plus 2 raised to the 2/3 plus 1. You can see here that at x is equal to negative 2, here my derivative would be undefined because of that cusp. However, that does not necessarily mean that this point right here is not, as you can see from the graph, this would be a minimum. So let's look at, if I didn't have a graph, how would I figure out that that is a minimum? So let's do what we did in the previous one. We're going to do the exact same thing, figure out when it's increasing, decreasing, and when there's a maximum or minimum. So let's go ahead and take that derivative. Because we have this rather function where you have the parentheses raised to a rational exponent, we're going to apply the chain rule here. So this is 2/3 times x plus 2 raised to the negative 1/3. That's it, because the derivative 1 is 0. This is my first derivative. Now if I rewrite this so that I can put the exponent positive and change it back to a radical, this would be 2 over 3 times the cube root of x plus 2. So again, because this is a negative exponent, I am moving this factor down to the denominator, and that exponent means that it is a cube root. So now as you can see, if we're trying to figure out when the derivative is equal to 0, that's when the numerator is equal to 0. But this numerator is never going to equal to 0. So instead, I'm going to figure out when my derivative is when my derivative is undefined, meaning when the denominator is equal to 0. So I'm going to take that denominator, 3 times the cube root of x plus 2, and I'm going to make this equal to 0. Even though this will make the derivative undefined, it is still considered a critical number. So we divide the 3, which is still 0. We cube it to get rid of that radical. And 0 cubed is still 0. So x plus 2 equals to 0. And then subtract the 2. So x equals negative 2. Again, just to reiterate, even though at x is equal to negative 2, my derivative is undefined, this is still a critical number. So now I'm going to create my number line with my only critical number of negative 2. Remember that this is my derivative. This is where I'm going to plug in my test values. A number to the left of negative 2 would be negative 3. The numerator will always be positive, but the denominator here is going to be 3 times the cube root of negative 3 plus 2. Negative 3 plus 2 is negative 1, and the cube root of any negative number will still be negative. So 2 over a negative would make this negative. And if I plug in a number to the right of negative 2, such as negative 1, this denominator would be negative 1 plus 2, which is positive 1. So everything would be positive. Therefore, this is positive. So now let's go through and answer all of these characteristics here. So f of x is going to be increasing on the interval negative 2 to infinity, because f prime of x is greater than 0. And you can see here on the graph from -2 to infinity, it is increasing. So we're using the graph here to verify everything that we're getting. Now let's move on to when the function is decreasing. Based on my number line, f of x would be decreasing from -infinity to -2 because f prime of x is less than 0. Now as you can see, here we only have one extrema. Because it changes from negative to positive, this makes it a minimum. So in terms of a maximum, we would say that there is no maximum because f prime of x does not change from positive to negative. Now for minimum, we have a minimum here at x is equal to -2 because f prime of x changes from negative to positive. Again, this should be reviewed because we've done this already, but it's nice to have the graph to just verify everything that we just said. Now let's look at what happens with the second derivative. So when you're taking a second derivative, you're just going to do the derivative of the first derivative. So the same process as you're finding the first derivative from the function. To get the second derivative, you find the derivative of the first derivative. So some things that we've been discussing. The first derivative of a function identifies intervals where a function is increasing, decreasing, has a relative maximum, or has a relative minimum. The second derivative identifies intervals where a function is concave up, concave down, or has a point of inflection. Now you're probably wondering, what is this concave up and concave down? So let me show you. This is the graph of some function. Now when we talk about concave up, concave down, we're describing the function's concavity. Concavity is which way is it facing. So concave up would be that it kind of looks like a cup. So like from here to here, in this section here, this is concave up. You see how it's like a U shape. From here to here, this is concave down. It's facing downwards. So it's like a U shape, but upside down. A point of inflection is the coordinate where the function changes concavity, which usually is right in between. So like right around here, from, if you can see my little arrow, right, to the left is concave down, to the right is concave up, and this coordinate right here would be considered the point of inflection. So let's get back to this lesson. If the second derivative is greater than 0, then what that means is that f of x is concave up. Now, just like the relationship between the first derivative and the function, right? The first derivative tells you if it's positive, the function is increasing, that relationship. It has the same relationship with the second derivative and the first derivative. So if the second derivative is greater than 0, that means that the first derivative is increasing. If the second derivative is less than 0, then that means that your function is concave down, which at the same time means that my first derivative is decreasing. So I kind of look at it like this. When think of it as like your function and then the derivative and the second derivative. The function that comes before, right? So like f prime of x, the function that comes before is f of x, or f double prime of x, the function that comes before is f prime. The one that comes before tells me increasing, decreasing if the function in front is positive or negative. So it's that relationship. If the second derivative is equal to 0, then that means that your function is changing concavity, therefore there is a point of inflection. And in terms of f prime, if f double prime of x is equal to 0, I mean, think of your first derivative. When your first derivative is equal to 0, that usually means that we have some kind of extrema. So that's what that is here. If your f double prime is 0, then my first derivative has some kind of extrema. Or rather, I'll say possible extrema, because it has to change signs. If the second derivative changes from positive to negative, whether it changes signs, this is all points of inflection. As long as your second derivative changes signs at all, that means that it's changing concavity. And you always have a point of inflection when your function is going to change concavity. So that's why all of these mean that there's a point of inflection. Now, if if your second derivative changes from positive to negative, then that means that your first derivative is changing from increasing to decreasing, meaning that there would be a maximum on the graph of the first derivative. If the second derivative changes from negative to positive, then that means that the first derivative is changing from decreasing to increasing, so there would be a minimum. So that's the relationship between a function, its second derivative, and its first derivative. So let's see how to determine concavity of a function. We've already done that f of x is equal to x plus 2 raised to 2/3 plus 1, and then we found the first derivative to be 2 over 3 times x plus 2 raised to the 1/3. And I want to figure out when this particular function is concave up, concave down, or where it has a point of inflection. So let's have a look. I need to take the second derivative, meaning I need to find the derivative of my first derivative. In order to find this derivative, I'm going to rewrite it so that it's easier for me to do so. This is 2/3. And then I'm going to bring up this factor so I don't have to use the quotient rule. So this would be x plus 2 raised to the negative 1/3. So now let's take this derivative. F double prime of x is going to equal to negative 2 over 9, because I'm using the chain rule here, x plus 2 raised to the negative 4 over 3, which I can rewrite this as negative 2 over 9 times x plus 2 raised to the positive 4 over 3. You can leave it like this with the rational exponent, or you can change it to a radical. Either way, an easy way of solving for our critical numbers here, again, the numerator is not going to equal to 0, but the denominator can equal to 0, and even though that would make my second derivative undefined, it is still considered my critical number. What I do is I basically ignore anything that's being multiplied on the outside of the parentheses and the exponent, because if I apply that to 0, like when I move everything to the other side, it would still be 0. So I just take what's inside of my factor and I make that equal to 0. So we still have our critical number at x is equal to negative 2. Now I'm going to create my number line, but this time my number line is using the second derivative. That's why I've always been on top of you guys to label your number lines, because now we're going to have two. We're going to have one for the first derivative, and we'll have a second number line for the second derivative. So a number to the left of negative 2, I'm going to plug in negative 3. If I plug in negative 3, I would get negative 3 plus 2, which is a negative number. Remember that the denominator is the root, and the cube root of a negative number is still negative. But then we would apply the exponent of 4, which would turn it into a positive because it's an even exponent. So this is going to be a negative over a positive, which makes it negative. If I plug in a number to the right of negative 2, let's say, for example, negative 1, this would be positive. And any positive number raised to an exponent would still be positive, so a negative over a positive would be negative. So we're going to use this number line now to answer these questions. When is the function concave up? The function is never concave up because f double prime of x is never greater than 0. Because in order for it to be concave up, the second derivative would need to be positive. When is the function concave down? This would be on the interval negative infinity to negative 2, and then negative 2 to infinity, because f double prime of x is less than 0. And then let's look at our graph here. Our graph, you see how it's facing downwards. It kind of cups downwards. So that's why it's concave down. And here, the same thing. It's cupping downwards. So that's why it's always concave down. Now for the final question, where is there a point of inflection? There is no point of inflection, because in order for there to be a point of inflection, your second derivative has to equal to 0 and it has to change signs. So we would say here f prime of x never changes signs. And again, by looking at the graph, we can see that at x is equal to negative 2, we have a cusp. So it's not differentiable for both the first derivative nor the second derivative. So impossible for that to be a point of inflection. A point of inflection would be something like this one right here, where you can see that on the left side, it's concave down, and then on the right side, it's concave up. Okay, so now we're going to put all of this together. We are going to determine the intervals where the function is increasing, decreasing, concave up, and concave down. And then we're going to find the coordinates of the relative extrema and any points of inflection. And of course, we're going to justify. And I gave you here the graph of the function so that we can verify all of the information that we're going to get. So let's first figure out increasing, decreasing, and all of that. So that is from the first derivative. So I'm going to take f prime of x, which is equal to 3x squared minus 12x plus 9. We're going to make that equal to 0. Now I'm going to factor. I can take out a 3, so this would be x squared minus 4x plus 3. And then I can continue factoring that to be 3, x minus 3, x minus 1. So we have two critical numbers here. That would be at x is equal to 3 and 1. Now I'm going to create my number line. And again, I'm labeling this number line. I'm going to plug in my test values. A number to the left of 1, I'm going to do 0. So this would be negative, and this would be negative, and negative times a negative is a positive. Then between 1 and 3, I'm going to plug in 2. 2 minus 3 is negative. 2 minus 1 is positive. Negative times positive is negative. And a number to the left of 3, to the right, I'm going to plug in 4. 4 minus 3 is positive. 4 minus 1 is positive. So positives all over the place, meaning it's positive. So let's write out what we know so far. We have that f of x is increasing on the interval negative infinity to 1 and 3 to infinity, because f prime of x is greater than 0. Then we have that f of x is decreasing on the interval 1 to 3, because f prime of x is less than 0. Now, it said here coordinates of any relative extrema. We have here, this one is a maximum, because it changes from positive to negative, and then this one is a minimum, because it changes from negative to positive. So we need to know what are the y values there for that coordinate. So we're going to take that x is equal to 1, and we're going to plug it in to the original function. So let's go ahead and do that. F of 1. This is going to be 1 to the third, which is 1, minus 6 times 1 squared, which is 6, plus 9 times 1, plus 1. 1 minus 6 is negative 5, plus 9 is 4, plus 1 is 5. So we have the coordinate here of 1, 5. Now we're going to do the same thing for f of 3, because I want that coordinate. If I plug in 3 to the third is 27, minus 3 squared is 9, times 6 is 54, plus 9 times 3, which is 27, plus 1. We get here that, whoops, got ahead of myself. 27 minus 54 is negative 27. Plus 27 is 0, plus 1 is 1. So we got the coordinate 3, 1. So what we got, we have a maximum, and based on my number line here, it is this one. So we have a max at 1, 5, because f prime of x changes from positive to negative. And then we have a minimum at our other coordinate, which is 3, 1, because f prime of x changes from negative to positive. So I got all that information just on my first derivative, but now we want to figure out the concavity. So I'm just going to shrink this so that way we have a little bit more space. If I want to figure out concavity, I got to take the second derivative of my function, meaning I'm going to look at my first derivative and take the derivative of that, which this is going to be 6x minus 12. I'm going to make that equal to 0. Add 12 to both sides, we get that 6x equals 12. And then divide the 6, we get our critical number here of x is equal to 2. We have one critical number. So now I'm going to create that number line. So f double prime of x, this will be 2. I'm going to plug in a number to the left of 2 and to the right of 2. So let's say if I plug in 0, this would be 0 minus 12, which is negative. And then a number to the right of 2, let's say 3. 6 times 3 is 18, minus 12 would be a positive. This is all I need. I'm ready to write out my concavity statements. So f of x is concave down on the interval negative infinity to 2, because f double prime of x is less than 0. And then f of x is concave up on the interval 2 to infinity, because f double prime of x is greater than 0. Finally, our points of inflection. We have a point of inflection when x is equal to 2. But again, we want that coordinate. So I need to find f of 2 to get the coordinate. I'm going to plug it in here. 2 to the third is 8. Minus 2 squared is 4, times 6 is 24. Plus 9 times 2 is 18, plus 1. 8 minus 24 is negative 16, plus 18 is 2, and 2 plus 1 is 3. So we have a point of inflection at 2, 3, because f double prime of x changes signs. Now let's have a look at all of this information and confirm it with our graph. We got that it's increasing from negative infinity to 1, and then from 3 to infinity, so that checks. We have that it's decreasing from 1 to 3. We have also the maximum at 1, 5, and the minimum at 3, 1. In terms of concavity, we have that it's concave down from negative infinity to 2. And you can see here how it is cupping downwards. And then we have where it's concave up from 2 to infinity, how it's facing upwards. And the point of inflection is at 2, 3, right where it changes concavity. So everything checks out. So if you're ever in doubt when you're doing all of this information, you can always go to desmos.com and graph the function and verify all of that information. All right, so now I know this looks really wordy, but there's a lot of things or a lot of information that we can get based off of a graph. So we're going to look at 3 different graphs. We're going to look at f of x, f prime of x, and f double prime of x, and see exactly how much information I can get from each one. We're going to start off with filling out these sentence frames about what the function tells us about the first derivative. So sometimes you may find it helpful to think of the reasoning before you look for the interval. Because if you know the reasoning, then you know what to look for on the graph. F prime of x is greater than 0 when f of x is increasing. So I work backwards sometimes with these. Now I know that on the graph, I have to look for when f of x is increasing, which it's increasing from the edge, so from negative infinity until negative 5. Oops. And then it's increasing again here at negative 2 until 1. Now f prime of x is less than 0, and this is when f of x is decreasing. So we're going to look on the graph for when my f of x is going down. We see here it's going down starting from negative 5 until negative 2, and then again from 1 to infinity. And you'll notice that all of my reasonings, when I write this out, has to do with the graph that you're looking at. So whenever you're given a graph, when you're writing out your justification for your answer, make sure that it's relating to the graph that's given. Now f prime of x is equal to 0, and you have a horizontal tangent when f of x has extrema. So I'm going to look for any minimums or maximums on the graph, which I have here 3, and these occur at x is equal to negative 5, negative 2, and 1. F prime of x changes from negative to positive at, now we'll figure that out now, but this happens because f of x has a minimum. And we have minimums here at x is equal to negative 2. F prime of x changes from positive to negative when f of x has a maximum, which you can see here we have 2 of them, which is at x is equal to negative 5 and 1. Now f prime of x is going to be increasing. F prime of x is increasing when your second derivative is positive. And if the second derivative is positive, that means that my function is concave down. Concave up. So you kind of have to talk yourself through this, right? In terms, remember that your function, your derivative will be increasing, decreasing, and has extrema depending on the concavity of your function, or rather depending on the sign of the second derivative. And the sign of the second derivative tells you the concavity of your function. So I'm going to look for when my function here is concave up, which it's concave up. We're going to have to make kind of an estimate here. Would be, I would say, right around here, because you can see here that it's cupping upwards, and then right around here is where it starts changing to concave down. So that would be, let's say, about -1 to 3.5, so -3.5 until about -0.5. Now f prime of x is decreasing when the second derivative is negative. And if the second derivative is negative, this is because f of x is concave down. And it's concave down the other rest of the time. You can see here it's cupping down, and here it's cupping down as well. So this would be from -infinity to -3.5, and then from -0.5 to infinity. F prime of x has a relative maximum. Okay, so again, we got to talk ourselves through this. Your first derivative will have a maximum if your second derivative changes from positive to negative. And if it's changing from positive to negative, that means that f of x is changing from concave up to concave down. So here's concave up, and then it changes from concave down. So the relative maximum for f prime would be at x equals -0.5. Now looking at f prime of x, it has a relative minimum. So again, minimum for the first derivative means that the second derivative changes from negative to positive. And if the second derivative changes from negative to positive, that means that f of x is changing from concave down to concave up. So here is concave down to then concave up. So then that means that this point right here, this would be the minimum of the first derivative, which is at x equals -3.5. Now if I look at these up here, f double prime of x is greater than 0. If f double prime is greater than 0, then that means that my function is concave up, which I've already identified. So a lot of these here, it's going to repeat what we have here, because this has the same relationship as these here. So f double prime of x is greater than 0 on the interval -3.5 to -0.5, because f of x is concave up. And f double prime of x is less than 0, and this is when it's concave down. So that would be from -infinity to -3.5, and then again from -0.5 to infinity, and the same reasoning as before, because f of x is concave down. F double prime of x is equal to 0, and the second derivative will equal to 0 when there's a point of inflection, and we have 2, which is at x is equal to -3.5 and -0.5, and again the reason for that is because f of x has points of inflection. So as you can see, this one graph tells me a whole lot. Let's look at the graph of f prime. So now we're switching gears a bit, and we're looking at the graph of the first derivative. So we're going to write information about the function and the second derivative based on this graph. So these are all things that we should know already because we've done this already in the past. F of x has a relative minimum at, and remember, think of your reasoning first if you find that helpful. F of x has a relative minimum when f prime of x changes from negative to positive. So we're looking at when this first derivative crosses the x-axis and it goes from negative to positive, which, as you can see, occurs here and again here. These are my minimums. So that is at x equals -3 and +3. Now f of x will have a maximum, and this is when f prime of x changes from positive to negative, which we only have one, which is right here, and that is at x is equal to 1. Now f of x is increasing. F of x will be increasing when f prime of x is greater than 0. So we're looking at all of the sections on the graph where it is above the x-axis. So that is this section here and this section here, so that interval is -3 to 1, and then from 3 to infinity. F of x will be decreasing, and the reasoning we know is because f prime of x is less than 0, and this is when your graph is below the x-axis. So that's here, from -infinity to -3, and then again from 1 to 3. Now f of x is concave up. So remember, talk yourself through it. It'll be concave up if the second derivative is greater than 0. If the second derivative is greater than 0, then that means that f prime of x is increasing. So now we have to look at when the graph is going up. And it's increasing from here to this point here, which is x is 1. So that is on the interval -infinity to -1. And then it increases again from this point, which is from 2 to infinity. F of x is going to be concave down when f double prime of x is less than 0. And if the second derivative is less than 0, then that means that the first derivative is decreasing. So we're going to look on the graph where f prime is going down, which is from here to here. So from -1 to 2. Okay, now we're going to see f double prime of x is greater than 0. F double prime of x will be greater than 0 if f prime of x is increasing, which is what we just talked about. So these intervals here are going to be the same as these down here, which if f prime of x is increasing, we wrote here the interval from -infinity to -1, and then from 2 to infinity. F double prime of x is less than 0, and this would occur when f prime of x is decreasing. Which we already stated is from -1 to 2. So what we use to talk ourselves through these two statements is actually the same as these two statements here, because if f prime of x is increasing, that means that f double prime of x is greater than 0, and vice versa. Now if f double prime of x is equal to 0, that means that my first derivative will have some extrema. So f prime of x has extrema. And we have 3 here. We have 2. We have this one here at x is equal to -1, and then we have the other here at x is equal to 2. Now that we've gone through the first derivative, let's look at our last graph, which is the graph of the second derivative. So now we're using this graph to talk about our first derivative and our function. Let's start down here. So the relationship between this second derivative and the first derivative is the same relationship as the first derivative and the function. So pretend like this is the first derivative and you're writing everything about the function, because that's the same thing. f prime of x has a relative minimum at, so f prime of x will have a relative minimum if f double prime of x changes from negative to positive. So let's look at the graph. That only occurs when you have your x-axis and you have changing from negative to positive, so from below the x-axis to above the x-axis, which we have this one right here, which is at x is equal to 0. Now here I gave you a freebie. F prime of x does not have a relative maximum, and this is because f double prime of x would have to change from positive to negative. But you can see on the graph here that the graph never goes from above the x-axis to below the x-axis. It only goes from below to above. So we would say here that f double prime of x never changes from positive to negative. F prime of x is increasing when the second derivative, f double prime of x, is greater than 0. So we're looking for when it's above the x-axis, which occurs from 0. We have to stop at 3 because it touches the x-axis, which means that the second derivative is, the second derivative is equal to 0, not greater than 0. So from 0 to 3, and then from 3 to infinity. F prime of x is decreasing when the second derivative is less than 0, so that's below the x-axis, which is from negative infinity to 0. Now these two here are tricky. F prime of x is concave up. F prime of x is going to be concave up if the third derivative is greater than 0, because it's how the relationship transfers over. So like if you have your function, the second derivative tells you concavity, and then it just kind of moves along. So if you have your first derivative, then its two derivatives after will tell you the concavity, which two derivatives after is the third derivative. So if the third derivative is greater than 0, that means that the second derivative will be increasing. So we would say here that f double prime of x is increasing. So we're going to look at where it's going up, which is going up from negative infinity to here, which is 1, and then from 3 to infinity. And same thing for f prime of x would be concave down when the second derivative is decreasing, because then that would mean that the third derivative is positive. And that is here, which is from 1 to 3. We're almost done. Here, f of x has a point of inflection. We only have points of inflection when f double prime of x changes signs, meaning either from positive to negative or negative to positive, which occurs only here at x is equal to 0. F of x is concave down as long as the second derivative is below the x-axis, because that would mean that f double prime of x is less than 0, which occurs from 0 to infinity. And finally, f of x is concave up when the second derivative is positive, so f double prime of x is greater than 0, which is above the x-axis. So from 0 to 3, and then from 3 to infinity. So that's all of the relationship. And I know that it's a lot, and it takes practice to see all of these relationships, but as long as you can remember that the derivative of anything is going to tell you increasing, decreasing, and then the second derivative is going to tell you the concavity, you can kind of talk yourself through all of these justifications. So let's practice. The function pictured is the first derivative of a twice differentiable function. When you see this twice differentiable, that just means that the function, we can take the derivative twice. That's all it is. So this is f prime of x. So let's see how we do here. Where does the graph of f of x have a relative maximum, minimum, and justify your answer? So a maximum occurs when the first derivative changes from positive to negative. So that means that we're looking for where it crosses the x-axis from above the x-axis to below the x-axis, which is right here. See, it goes from positive to negative. So that is at x is equal to 0, and we would say because f prime of x changes from positive to negative. Now for the minimum. We have a minimum when the first derivative changes from negative to positive, which we have one here, see, negative to positive, and then another one here, negative to positive. So this is at x is equal to negative 2 and 1 because f prime of x changes from negative to positive. Where is the graph of f of x? Concave up, concave down, and justify your answers. So let's look for concave up. So let's talk ourselves through this. We know that our function is concave up if the second derivative is greater than 0. And if the second derivative is greater than 0, that means that the first derivative is increasing. So this means that it's increasing here, and then here it's increasing again. So when we're writing our intervals, remember that it's always the x values. You have the coordinates, but we don't care about the y. We just want the x's. So it's concave up from negative infinity to negative 1.215, and then again from 0.549 to infinity because f prime of x is increasing. Now for concave down, that means that our graph for f prime of x would be decreasing, because if it's decreasing, then f double prime of x is less than 0, which tells me the concavity. So, and that would be from those x values, the negative 1.215 to 0.549. And our reasoning would be because f prime of x is decreasing. Finally, find the x values where f of x has point of inflection and justify your answer. So points of inflection occur when the second derivative changes from positive to negative or negative to positive, just changes signs. And if the second derivative is changing signs, that means that the first derivative is either changing from increasing to decreasing or vice versa, which indicates extrema. So we're looking for the extrema on our graph, which we have here and here. Those are my extrema. So we have points of inflection at x equals negative 1.215 and 0.549, and our reasoning would be because f prime of x has extrema. All right, almost at the finish line. Let's look at a couple of these multiple choice questions just to make sure that we truly understand. We haven't really looked at any charts in this lesson, so I threw one in there to see how we do. The derivative g prime of a function g is continuous and has exactly 2 zeros. Zeros, remember, are your x-intercepts. Selected values of g prime are given in the table below. If the domain of G is the set of all real numbers, then G is decreasing on which of the following intervals? Okay, so what this means, if the domain of G is a set of all real numbers, that means that the graph opens forever left and forever right, so the domain is negative infinity to infinity. That's all that means. To figure out if it is decreasing, it's decreasing as long as g prime of x is less than 0. On this chart, we have all of our x values and we have all of our values here that are important for g prime. Sometimes we get confused looking at charts, so I like to translate my chart to a number line. We need our critical numbers. And our critical numbers occur when our first derivative is equal to 0. So we have one here, because this is 0, and we have another here. So that's from negative 2 to 2. And now I'm going to look at my derivative values. Think of these as like your test values to fill in the signs. So to the left of negative 2, we got positive numbers. Between negative 2 and 2, all of these y's here are negative. And between 2 and 4, everything after that is positive. So if we're looking where it's decreasing, we're looking for when this is less than 0, which is on this interval here, between negative 2 and 2, which is option A. Last question. The second derivative of the function f is given by f double prime of x is equal to x times x minus a times x minus b squared. The graph of f double prime of x is shown below. For what values of x does the graph of f prime have a relative maximum? Okay, so let's talk through it. F prime will have a maximum when f double prime, remember it's always the derivative after, talks about maximums and minimums, changes from positive to negative. So we're looking here, because this is the graph of f double prime of x, as indicated in the question. We're looking for the points where my graph changes from above the x-axis to below the x-axis, which we have here from positive to negative here at A. This goes from negative to positive, and this doesn't change. This goes positive to positive. So we only have one maximum for f prime, which would be at A. So to kind of summarize with anything, when you have a graph or an equation or whatever, the derivative afterwards tells you increasing, decreasing, and extrema. And two derivatives after that tells you concavity. So just keep that in mind. And that's the relationship between a function and all of its derivatives.